Hi everybody, this talk is going to be in English as planned, as I hope it's okay for everybody. So my name is Marta Rivera and what I'm going to talk to you about today is who I am, the things that I do, and the tools that I use to do them. Basically the tools that I'm going to explain you today are all the Python packages that I combine and that I suffer with every day of my daily job. So first, who am I? I'm a physicist by training. I have a PhD in neuroscience that I did half in Madrid, half in Washington, D.C. During my PhD, I proved that a small part of the brain of flies is actually optimally organized to perform its function, as crazy as it sounds. After the PhD, I moved to Portugal and again to the US to analyze the behavior of animals. I developed computer vision and machine learning tools to analyze the behavior of 47 species of larvae, and we were comparing the behavior of all those species to understand which parts of the behavior were kept during evolution and which one were changing from species to species. So I've worked in academia for longer than I'm gonna admit today. Always developing mathematical tools, computer vision tools, and machine learning tools to analyze either the anatomy of the brain or the behavior of animals. And for almost 2 years now, I have been working on a different behavior, that is the behavior of the market, and at ETS, and I will get into a detail of that in a second, and I also teach statistics in that university in Madrid. Can you hear me at the back?
No, not really.
Can you move to the front? There is a mic here, but I think it's for the camera. So, hi, closer people now. So I was saying, this is who I am. I'm a physicist. I'm not a programmer. I was never a programmer, and I doubt I will become a programmer anytime soon. But I work with code every day. That's why I'm here, because I work with Python every day. So this is who I am. So, but what do I do? As I mentioned, I work at ETS. ETS is a financial company. We develop mathematical models to analyze the behavior of stock indexes, currency pairs, things like that. Me specifically, I work on developing machine learning tools to analyze the behavior of stock indexes. What we do at the end of the day, or at the beginning of the day actually, is giving a signal to somebody in Switzerland to tell them buy or sell this specific index. I'm going to explain you just 2 or 3 things that we have developed in the group in the last year and a half, because I believe they may be interesting to you, because we actually use machine learning tools for that. So the first one is to expand this definition. In general, in finance, we define bullish and bearish markets as the index or the stock going up or down. So it's basically based on just one feature that is either going up or down, right? That's all. We thought we could do it much better just by adding more characteristics to the analysis. So we calculate hundreds of characteristics, rolling characteristics as we call them. So you basically just compute them in windows and move them forward in time. And with the simplest algorithm you can think on, we define clusters in that multidimensional space where all those data points now live. And that allows us to train a supervised algorithm afterwards to detect those specific regimes, those rich regimes, instead of just going up or down. This system is completely unbiased by humans because the origin of the clustering is unsupervised, but because we combine it with a supervised methods afterwards, we can actually detect them every day with that automatic definition. What is the interesting thing about this? First, as far as I know, it was not done before. That's always a breakthrough. Then we have to prove that it's actually useful, but at least we did it first. And the nice thing now is that we have a much complete representation of the environment, the context of that specific day. So we can adapt our methodologies way better to uptrends with a specific volatility that is super important in finance, or specific efficiency going in that up or down, or staying in an intermediate range market. So as I mentioned, we do this so we can adapt our methodology, and we also went one step further than that, and we invented another methodology to do that strategy allocation automatically. In this case, this is an example for technical models. They are super used in finance. They are signals based on this very feature engineered indicators, actually, that people applied on those indexes, and I apply on those indexes too. So this first one is actually a TSNE embedding. If you don't know what a TSNE embedding, it doesn't matter. This is a two-dimensional representation of a 37,000 dimensional space, where each dot here is just one technical model. It's actually the behavior on one technical model on the graphs in the right side. We clustered these guys also with very simple technique. This is actually an spectral clustering, I recall. And we combine the signal coming up from all those models. So we have a little extra sensitivity there. And automatically, again, we select a collection of models that is of our interest. The nice thing here, as I mentioned, is we can do this automatically by doing a smart ranking based on boosting. If these words don't mean anything to you, it's fine again. Basically, what we do is we design specific metrics that are encapsulating all our intuition, all our needs, or what these models should be doing. And we use those metrics to select them. Just with regular ranking, you can ask me all the questions you want afterwards, because I think we will have enough time. So machine learning here is allowing us to do two extra things that are never done before, or not done normally. That is defining those extra market regimes, and allowing us to assign our strategies automatically. It doesn't require any manual processing, any manual bias anymore. So this is what I do normally, but how do I do it? I already mentioned that I use Python. All those plots were actually done in Python by us. All the computation behind is done in Python. And I mean, I don't need to explain you why. This is the nice thing about the Python, that I don't have to explain why we use Python. The powerful thing about Python is that it includes range of packages with all possible combinations of utilities, calculations, and tools that you may need. And what I'm going to do now is I'm going to explain you which is the list of packages that I normally use. I don't mean to show you all the possible Python packages. That would be like impossible. And I don't even mean these are the best ones. These are the ones that I'm currently using. This list gets updated frequently. And I also actually thought this morning that I forgot about one that I normally used to. So it gets updated frequently, and some of them gets deprecated fast because I tend to forget that I use them the next day, and then I look for a new one that is slightly better. So this is not a fixed list. That's what I mean. It's just the one that I'm currently using now. So first, to do data science, I mentioned, I hope, that I was a data scientist. Data scientists work with code all the time, but we don't develop code, or we shouldn't. Our goal is completely different. So our tools, our IDE, should be different too. I would recommend you, because it's what I use, and I think it's the most effective way of analyzing your data, to use IPython, to use an IPython kernel. IPython allows you to interact with your code line by line, and it also allows you to plot wherever you want, just by your code, and to keep a history, actually, of what you are doing with all your plots, with all your code, all your interaction. To work with IPython, you can either use JupyterLab or Jupyter Notebook. That is more famous. JupyterLab is just the DG evolution of Jupyter Notebook. And I personally like Atom with hydrogen more. That is actually a screenshot, a print screen of my screen at work, because I couldn't find a nice Atom plus hydrogen picture, so I just did print screen, and that's what we got. Because JupyterLab, at least under my experience, it has a little bit of overhead, and it collapses my memory. I collapse memory on a daily basis, so I want that not to happen that often, and that's why I use Atom. JupyterLab, like Jupyter Notebook, has those small cells that you can run individually. In the Jupyter, in Atom, you run each line individually. I mean, the forks are run in one piece, but it's the same idea. It's an IPython kernel that I encourage you to use instead of using PyCharm or the Notepad that I used to for a while. I would recommend you to do use some of these guys. I encourage you to try the one on the right, just because it's less known. So, data science. When we talk about tools for data science, first we need to understand what data science is. I have complicated definitions on things because I'm coming from somewhere else always. I'm in the wrong field all the time and changing fields every 2 years. So I always get crazy ideas about what things are, but I have been working on science of data or analysis of data for long enough to have a pretty, broad, that was the word, understanding of what it is. So to understand what data science is, we have to think on the fact that there are two words there. The first one is science. So when we talk about science of data science, what do we actually mean? I mean, we mean scientific method, right? The scientific method, when you design a hypothesis, then you do some experiments, then you test your hypothesis, and you get a result. And then you publish a paper, hopefully, as high profile as you can, hopefully. So the scientific method, I know is not the thing you first think when you think about data science, but please don't disregard the power of science in data science. It has a little problem. It requires you a lot of knowledge on the field. Regular data science too, but it requires a very specific knowledge. And of course, the first thing that you do is ask a question, formulate a hypothesis. There is no Python tool for that, just pen and paper. And a lot of time, and a lot of reading, and a lot of talking to your colleagues. Please don't disregard the power of scientific method. When you ask a question, you are a step closer to the answer. This is the way science has been done for a long time, and it's still the nicest, more elegant way of doing science. I would recommend you to try from time to time. So once we have our hypothesis, we can do our experiments and then import it in Python. Then we start talking about Python packages. This is the usual suspects. We use NumPy, I use NumPy, Pandas, in general the whole SciPy package. You take your data, you take a look, you make sure your data is clean, you don't have weird numbers, you paste it correctly, you can import it. Actually, Pandas is very nice because it has all those importing tools from Excel, if that is your favorite thing, or CSV, or whatever other method, or text files. Also, our data is also in text files. You can also import your data through, it depends on when you take it, from the web or from your own experiments, or from APIs that I heard that yesterday there was a very nice API talk here. I hope you went. Once you have all your data in your computer, you formulate your hypothesis. I mean, you test your hypothesis that you formulated at the beginning. Very standard, very powerful statistical package for Python is stats models. Instead of using SPSS or some other things you might have heard of, stats model is actually quite powerful. You have all the usual hypothesis testing, binary, things like that. And finally, you present your results. Depends on what is the way you are allowed to present your results, because sometimes we don't choose. I mean, if it's a scientific paper, it has to be static images, so I would go for Matplotlib. And I would recommend you haven't tried, to use Seaborn on top of Matplotlib. It has way nicer plots, way nicer, the colors are just nicer. And surprisingly, that Seaborn is written right there, that's their logo. But I promise that the package is better than the logo. It's much nicer than the logo. Actually, for example, I don't know if you try plotting box plots in Matplotlib, it's a nightmare. In Seaborn, it's very nice. So if you ever have had that problem, you can try, it's much nicer. If you can present your data in an interactive way, I would recommend Bokeh. It's fantastic, it's beautiful, works nice. And if you can go even further and present your data as a nice web page, you can use Dash by Plotly. I haven't used it myself. I'm just amazed by their web page. So I would recommend you to take a look and be amazed by their web page as I am. So this is about science, but what about the other world? What about data? That is actually the most typical definition of data science, right? Is that data-driven research. When the data is giving you the knowledge, you don't have a prior information, you have a prior hypothesis of what you are going to find in that data set. It's also called exploratory research. Some people use it to define hypotheses, then to try the scientific method, right? To try to test it. So they are not completely independent. I like to call this ignorance-driven research. And this is not disrespectful, I do it all the time. But I call it ignorance-driven in opposition to that I know a lot about this field and I formulate a hypothesis. Here, we don't know anything. We just have a bunch of data. And we want to know what that data is telling us, right? We don't have a specific, a priori model describing the world. We want the data to tell us that model, to learn that model. And that process of learning a model that describes the world from data is called machine learning. And that's why machine learning and machine learning tools are fundamental for data scientists. So which tools we can use here? The beginning is almost the same as before. You can import your data. I mean here data science, not big data science. That will be in the next slide, so don't panic for a second. Again, we have NumPy, Pandas, and the whole SciPy package to load your data, to take a look, to make sure your classes are balanced, to make sure you don't have outliers, to make sure you don't have, or you have missing values, to make a decision on what to do with those missing values, if you want to infer their value, things like that, to make sure all your columns are valid, and your data set is large and clean, and you clean it and organize properly. If you work with images, you can take a look at OpenCV Python. There is a specific Python package of OpenCV that it should work like the rest of the OpenCV packages of our libraries. And Scikit-Image. I haven't used it, but it has a very nice web page. And I learned that one of the contributors is a former colleague of mine. So you have it there, you can try. So something that is not that useful, and if I can give you a piece of advice today, it would be this one, so pay attention now, is to plot your data before training your model. That's why I have that intermediate step with Matplotlib or Bokeh that allows you for the interaction, as I told you. Take a look at your data. Look at it. When you plot, you can do histograms to make sure your trained tests are in the same ranges. You can do scatter plots against your label if your problem is supervised. You can start having an idea of how complex you need your model to be. It's always, the best idea is always to go as simple as possible. I'm a physicist, I believe in spherical chaos. This is not useful for everybody, but this is another recommendation that I have for you, to go as simple as possible. But take a look at your data. Look at it, plot it, and analyze it by eye. We have a lot of intuition, and at the end of the day, you have to choose a model you are going to train, right? the more information you have about how your data is organized, the easier it's going to be to find a nice model for a nice algorithm for your data. So to train models, the king is scikit-learn. Of course, it's in the list. I should tell you, if you don't know, that scikit-learn is actually running a lot of SciPy tools, a lot of SciPy functions behind. By the documentation of SciPy is a nightmare. It's impossible to parse, but the scikit-learn documentation is beautiful. So we are actually many times running SciPy, sometimes without knowing it, SciPy algorithms through scikit-learn. If you want to try a very large neural network, you should go for TensorFlow. In this case, large or not very deep, because we are still in not big data science. TensorFlow, I run it through Keras. That is kind of a wrapper of TensorFlow that is easier to install. You lose a bit of the specific details on every single parameter of TensorFlow, but it works for me. It doesn't work for everybody. And finally, if you want to run boosting trees, you can go for light GVM or XJBoost. This is the first time that I pronounce this word in English. We just won the hackathon, the Python hackathon with light GVM 10 minutes ago. And the guys that won the happy hour yesterday used XGBoost. They are very powerful techniques for training random forests and random trees. And to present the results, again, the same thing. You can use Matplotlib, Seaborn, wherever you need, depending on how you are gonna represent your data. And as I mentioned, I keep the idea here that your data fits in memory. If your data doesn't fit in memory, you have to go one step further. And this is something that I actually think that big data people didn't think through. So they have done something for us that make us don't need them anymore. I don't think that's a good career move. But in any case, they gave us that present that is Dask. Dask has NumPy-like, Pandas-like data frames and arrays, and scikit-learn that allows us to interact with our data as if it's in our computer when it's in the network. I'm loving it currently. Dask actually works super nicely with scikit-learn and TensorFlow and makes the whole interaction, actually TensorFlow is easier to use through Dask, or with Dask. You should try, you should give it a try. And the rest of the process is the same. All those algorithms, I mean, to present your result, you shouldn't depend on a big network. You should have a result that is nice and clean and small. Okay. I hope you liked my zoo of tools. These are all the logos here. You can take the picture. I think this is the picture. The picture now. I hope you like my zoo. I hope you like my pets, and I can take questions now.